Right, okay. Right, everybody, what we're going to have a look at today is the sigma notation. Now, has anybody ever heard of the word sigma?
Yeah.
Anybody?
Yeah.
Right, so in what context have you heard of the word sigma, Bryant?
Physics.
Physics, and what was it referring to?
Sum of all.
The sum, right. Okay, now, the sum. And what was the symbol? Was it... Right, so it was like a... If you turn around, you can have a little look on the poster. We've got a letter sigma on the Greek letter sigma there. We've got a picture of it. Now, has anybody else ever heard of the word sigma? Right, what have you heard it? Exactly the same. Right. Okay, now have you done standard deviation at any point? Yes? So you've done that in mathematics with in the other side of the maths. Right, now did Mr. Hall introduce the symbol sigma?
Yes.
Yes, now, what was that used in reference to? Do you remember, Tang, what that was used in reference to?
I don't remember.
Right, well it was used in reference, referring to the value of the standard deviation, but you didn't use it, the same symbol for the sum and for the standard deviation. If we look at the differences, this is the capital letter sigma and this is the small letter sigma. Now, this one is used in mathematics to represent the sum of. So it's a shorthand method of representing adding up a number of different things with similarities. We'll go on to have a little look at that in a minute. Whereas this one is used to represent the standard deviation value. So if we're referring to the standard deviation, this is the symbol that we can represent it as. Okay, so sigma is a symbol for the sum of terms. Now what we mean by that, it's written in this context. So you have, almost like we have an integration, you have sort of a top and lower value. So R refers to the range of values that it can actually take. So R is ranging from 0 to 6. And what we're basically going to be doing, we have a formula, 2 to the power of R, and R will increase in turn using the integer values, going from 0 to 6. Now it doesn't necessarily have to start at 0, it could in fact start at 1, but that information would be provided with the lower value here. So it would perhaps say R equals 1 to 6 at the top. So you have to use that in order to work out what your starting value is. The formula that you're going to be using is always here, and that will be in terms of R. Okay? So what we're going to be doing is in turn substituting in the values 0, 1, 2, 3 and so on until we reach the uppermost value. Okay, right. So what would all of that come to? Let's have a little look. If we put this in turn, then when we insert the first value, substitute in R is 0, we get 2 to the power of 0. Now, what is 2 to the power of 0? 1, right. And then we get 2 to the power of, when R is 1, we get 2 to the power of 1. What is 2 to the power of 1? 2. 2 to the power of 2, 4, and so on. So we will then have to add it up. Now this can be quite a tedious process. So what we would do is look for shorthand methods. Now what shorthand methods have you looked at recently to add up large sequences of numbers? Nikki, what have you looked at recently that would help you to add up large amounts of numbers? What did we look at recently? Arithmetic. What do we call them? Arithmetic? Progressions, well done. Arithmetic progressions. And Brian, what was the other sequence that we looked at? Geometric progressions. Now when we studied those, we had a couple of different formulae which assisted us to add up large quantities of numbers. So that might be something that you might want to bear in mind later on when you come to add up, rather than just simply have to add these up using your calculator. What type of sequence is this one on the board? Oswald, have a little look at it. What type of sequence is it?
geometric progression.
It's a geometric progression. So rather than simply work with your calculator, if you had an awful lot of numbers, like here you've only got 7 different terms, but if you had a lot of numbers, you wouldn't want to have to sit through and add those up, would you? Be very tedious. So look for shorthand ways of doing it, please. Right, okay, now this could be quite a useful way of adding up numbers where perhaps, or indicating a sequence where there's no terminating value, all right? Something like this, where the sequence doesn't actually end, all right? You haven't got an end value. So what we could do here is we could start off with r is 0. Let me remind you, it doesn't have to start at 0. It could start at 1. It could start at 2. You could choose your value, okay? Up to an infinite value, all right? So when you see dots, then you need to look at the uppermost value as being the infinite value, please. Right, now this is, what type of sequence again, Dan? What type of sequence are we looking at here? A geometric progression. So we would be looking at, what's the general nth term of a GP? What was it? Have a little think. What was the nth term that we looked at yesterday?
A times r, the n minus 1.
That's right, a to the r n minus 1. So what was the r value? What was our constant ratio value? Bryant, what was our constant ratio value in this sequence?
Times r.
What was the value? What was our ratio value with this sequence? 1 over 2. So r was 1 over 2. What was our a value, Lorraine? 1. Okay. So you can see why the formula, hopefully, you can see where it's originated from. Because our a value, we don't have to obviously put it in because the 1 doesn't help the formula in any way. Okay. How would we get this to alternate sign? What if it wasn't all pluses? What if it was plus minus plus minus plus minus, or minus plus minus plus minus plus? Have a little think. How would you do that? Anybody? How would we get the sign to alternate in a sequence like that? Peter?
The common ratio will be minus, will be negative.
Right, the common ratio would be minus, so we might be able to incorporate it into the common ratio. So that might be one way of doing it. But we've got to be careful that it might not necessarily line up with the same value r. Right, because what are we going to be raising to a power of r? What value? Max, what do you think? How are we going to get this to alternate? Or Zaid, how are we going to get this to alternate?
We could possibly have a negative value for r.
So this is what Peter was saying. We could have...
I thought you said the common ratio.
Yeah, so the... Right, so the... Oh, right, so we could have a negative value. But that's always going to be increasing, isn't it? From a lower value up to an... I don't think that's necessarily going to give you alternating signs. Minus in front of 1 over 2. So again, you want to alter the common ratio. Anybody got any ideas about... Think about powers of negative numbers. When do we get positive numbers? When do we get negative numbers? What about when we square and cube positive and negative numbers? Janning? When do we get a positive number? If we've got minus 2 and we perhaps square it, and then if we've got minus 2 and we cube it, what's the difference? What's the difference in the two outcomes? I'm not so bothered about the numerical outcome, I'm after the sign. What would you get with the top one? Positive or negative?
Positive.
Positive. So you've got positive. And what about the bottom one?
Negative.
Negative. Right, what's the difference? What's the difference? Why did you get positive in the top one?
Because the power is even.
Right, the power was even, wasn't it? And how did you get, and why did you get negative in the bottom one?
The power is
the power was odd. Right, so that's what we need to incorporate into this work. We need to try and incorporate that. So, how can we do that? What do we need to raise to a power of r? What value? So, oscillating terms, if we firstly think of it as altering, as considering the oscillation with just simply minus 1 to the power of r. But if we want to, if we're talking about r being 0 to infinity, will it be plus or minus to start with? If it starts off with r is 0 to infinity, will that be plus or minus to start with? That will be plus to start with. What if it was r is 1? Minus. So that's one way of altering it. But what you've got to ensure is that what works with that also works with the rest of the sum. It's got to work with both parts. So you can't just put a blanket minus within your common ratio because it doesn't always work in exactly the right way. You've got to be careful. So please be quite cautious with that. Let's have a little look at an example. Right, so what we've got there, if we again we're starting at r is 1, this one would give us because we're starting at r is 0, this would give us the positive term first. And r is 0 would ensure that we've got 1 over 1, so we've got a first term of 1 here. Our second term would be r is 1, so it would be 1 over 2, and we would then have an odd, sorry, r is 1, so we would have an odd sign. And then when r is 2, we would have an even sign, r is 3, an odd sign, and so on. So we'd get an oscillating sign happening. Okay? Right. Now, how would we write this one? What would we do for this one? How could we change the summation to give us this one? So now we've got the difference in the sign. Any ideas? What would we do with that one?
Start with r is 1.
So we could either start with r is 1, but that would alter the numerical values. So you can't simply just do that. Because if we just alter, let's just have a little look and see what the implication of that is. If we start with r is 1 to, not 2, what would we have to have as the top value then? R is 1 to 8, all right? R is 1 to 8. Well, firstly, I can see that there's a problem already because your last term is going to be 1 over 9, isn't it? If you don't alter anything else. So you're going to have to adjust something.
Yes. Is it something to do with minus 1 to the power of r plus 1?
You could do that.
Yeah.
That's exactly right. So what you could do, you could leave the limits as they are and alter the formula. So if we leave the limits as they are, r is 0 to r is 7, exactly the same as they were. Let's go with what Max just said. If we say minus 1, what did you say? R plus 1.
Yeah.
All right, that's going to alternate it on the other number now, isn't it? It's going to add 1. So what would have been an odd power is now going to be an even power. What would have been an even power is now going to be an odd power. Okay, so that will work, but we're not actually changing the numerical value. So 1 over r plus 1, that's still staying the same. So that's one way of doing it. Alternatively, anybody got another idea? Let's go back to the changing of the limits. R equals 0. We don't have to go up to 8, however. Sorry, r is 1 to 8. Send this up. R is 1 to 8. If we just leave this alone now, that will correct the sign, but what will we have to do to correct the rest of
We
it?
just need 1 over just r.
1 over r.
Yeah.
So That's why I said earlier you had to be cautious about just simply putting a minus in front. Okay, now I have notes on this to hand out to you. Okay, so there's backup notes for you to have a little look at afterwards. Does that all make sense? Right, now what I want us to do is to have a little look at a couple of different examples. Now the examples I want you to have a go at are these. So we'll do them together. You have a go at them first. Okay, let's just have a little look at this. Now, there's a couple of different ways of doing this one. What we're after is the nth term, because what you're trying to do is come up with a formula for the actual term in terms of r. Okay, ever changing r. So, first of all, you have to try and work out what type of sequence it is. So, Sam, what type of sequence was it? AP or GP?
Oh, it's AP.
It's an AP. Can you create a formula for each term number? What's happening each time?
Increasing by 2.
It's increasing by 2. So what would be the general formula for the nth term?
It's just 2R.
It's just 2r, isn't it? It's just 2r. It's not a complicated one, this one. Now, we've got a choice. If we're saying 2r, what are we counting r from? R is what to what?
1 to 10.
R is 1 to 10. Okay? Now, that's the most straightforward way of writing it. Everybody happy with that? Yeah? There are different ways of doing it, but you would have a more complicated expression. If you were to start at r is 0, then you wouldn't be able to just write r here. You would have to write something, you would have to write r plus 1. So it's more complicated. So you always should be going for the most straightforward way. Okay? Second one. Right. Janning, AP or GP? AP. Right. Have you got an nth term formula for that one? If you're having difficulty coming up with an nth term, you can always create the nth term using the methods that we did last lesson. Create the A value, create the D value, and it's more difficult to, obviously we don't know how many terms there are, but we come up with an N value for the term number. So can you see what pattern is developing? What's it going up by each time? 5. So what's going to feature in the formula? 5. Should we do it with the nth term? So what's the A value and what's the D value? What's the A value?
4.
A is 4 and the D value is 5. So if we are creating the nth term, the formula that we're using is A plus m minus 1d. Alright, so if we substitute in, then 4 plus m minus 1 d. Simplify that, what do you get? 5n
minus 1.
5n minus 1. Now if you look at the formula, 5 ones are 5, take away 1 is 4. 5 twos are 10, take away 1 is 9. 5 threes are 15, take away 1, 14. Okay? So, when we write this as a formula, we don't use n, what do we use? We use r. Right, Bryant, if the formula is 5r minus 1, what will our limits be?
1 to n.
R equals
R
1.
And then
N, we have
infinity.
an infinite series, so we need to put infinity as our top limit there. Is this still an AP or a GP, Bryant? AP or GP? What do you think? What do you think? AP, well done, AP. So, is it a simple formula? Lorraine, what do you think? Have you got the formula? No? Think about what's happening each time. If this number was 1, 2, 3, 4, can you see a simple way of getting those numbers? Multiply by 3. Yes. Sometimes that's all that's necessary. Just have a little look at the counting integers and see if you can spot a rule. Sometimes that's the easy way of doing it. Failing that, then once you've ascertained that it is in fact an AP, what you then need to do is work out A, work out D, and N will just be your R value. Okay, and put that into the formula and simplify. That's all that you would normally do. So A is 3, D is 3. If we put that into the nth term, then you get 3 plus R minus 1 times 3. So 3R is all that remains, 3R. Okay? So, the sum of, what will our limits be? Oswald, what do you think? What would our limits need to be with this one? R is 1 to infinity. Now, I haven't accounted for the fluctuating sign, for the oscillating sign. So how do I account for the oscillating sign? Who's going to do that? Minus 1 to the R. Let's just make sure that this is actually giving me the right sign. If we say minus 1 to the R, is it negative first?
R plus 1.
Minus 1.
Right. Minus 1 to the R, minus 1, or minus R, plus 1. Either way will do. But you can't leave it as R. You have to have that either plus 1 or minus 1. Because if you leave it as R, what's going to happen, R will be 1 to start with, you'll have minus 1 to the 1, which will give you a negative to start with rather than a positive, and that's not in fact what you want. So if you put R plus 1, that will work, alternatively R minus 1 will work, but the choice is yours, either way. Sometimes if you've already got an R minus 1 in the formula, it makes sense to call it R minus 1 because then you can group it with the bit that you've already got and then group that term to simplify. What I would tend to do personally is to treat this as a GP and treat the sign separately, okay? So if we were just dealing numerically with this example, then what would the formula be for the GP? What would the formula be for the GP if you were coming up with the nth term, Pete?
2 times 3 to the power of
2 times 3 to the power of
R minus 1.
R minus 1. All right, nth term of a GP. Everybody happy with that? Right, if we then need to deal with the minus, and what would you choose as R? R is what to what?
1 to infinity.
R is 1 to infinity. Right, R is 1 to infinity. Right, Zaid. We want it to oscillate on the first, the third, the fifth, and so on. Right. What do we need to do to make sure that it oscillates on the correct term number? What do we need to ensure? If we put minus 1, what do we need to make sure?
So for the, we need to make sure that the numbers, the power you're raising to, if that's odd, then that would mean that the numbers should be negative because a negative power, or an odd power of a negative is a negative.
Right, so an odd power of a negative is a negative. So therefore, do I need to put this as an R or an R plus 1? So if I started off as R is 1, so do I need to put this, make this an R or an R plus 1?
Just an R.
Just an R. Okay. Now, that would be your formula for the nth term, for the sigma, for the sum of the n terms. Okay? And you would leave it as that. Right? If these powers happen to be the same power, you could group them, but treat them separately. Treat them separately, and that way you get it oscillating in the correct way. Okay? Right. What I want to do now is for us to move on and just have a little look at some numerical values. Some other different types of examples. Okay. So we've spent a bit of time practicing types of questions where you've had to come up with a formula. Now, a lot of the time you are just utilising a sigma formula. Right, so if you could just stop what you're doing a couple of minutes, please, and just look at the board. Right, so we've got some examples here, which we're just going to look through, and then we'll have a look at some different examples, some different exercises. Right, if you're asked to calculate the summation, now you've got 20 terms there, haven't you? Now, nobody wants to have to add up 20 numbers, ever. All right, it's very, very tedious exercise. So let's first of all just generate the sequence. Looking at this formula, what type of sequence is it? Anybody? What type of sequence is it? We've been looking at sequences. An arithmetic progression. Okay, this is an arithmetic progression. So what would be the first term? It's ranging from r is 1 to r is 20. So what's the first term of your arithmetic series? So r is 1, so 4 times 1 is 4 plus 1 is 5. Okay? Plus, because this is a summation sign, the second term, 9. The third term, 13. The fourth term, 17. Right, now I'm not going to go any further, but I am going to look at the last term. What would the last term be?
81.
81. Right. Now, I don't know about you, but I do not want to, two things, I don't want to work out all the terms, and neither do I want to have to add them up once I've worked them all out. So, let's think about ways that we can add up those numbers quickly. What have we learned recently that will add up all of those numbers? The sum of the AP, good. Right, remind us then, Sam, what is the sum of the AP? Right, sum of the AP.
N over 2.
Good.
Brackets. 2a, yeah.
2a. Good.
N minus 1.
Good. Multiplied by d. Good, well remembered. Okay, so that's your sum of the AP. So what you do, once you've got your sum of the AP remembered, then you take from the sequence, you take your value of the A, you take your value of the D, and you have a look to see how many terms you were looking at. Okay, so let's get that information. So what is your first term then? 10. What is your first term? What's your A value?
5.
5. Right, Ryan, what's your D value? Yes.
4.
4. Brian, how many terms have you got? 20, good. So what you then do is you substitute all of this information into the formula to come up with the sum of the 20 terms. Okay. So, substituting in 20 over 2, 2 lots of A, which is 10, plus n minus 1, so that's 19 lots of 4. Right. So you've got 10 plus Right, 90 lots of 4, 70, 76. So we've got 86 times 10, 860. Okay, so that's how we can utilise the formula that we learned a couple of lessons ago in order to make our life much more straightforward today. Okay, happy with that? Yeah? Right. Have you all finished copying that down? No? Did you say yes or no, Brian?
Yeah.
You have. Okay. Right. Okay. Right, let's have a little look at the next example. Similar type of question, very different sequence. What type of sequence is this? If you're not sure, you need to generate a few terms first to see what it looks like. So, who wants to start us off on the sequence? What does it look like? What type of sequence? Nikki, what do you think?
Geometric.
Geometric progression. So what would be the first term then?
Just substitute k with k equals 1. So that is 5.
That's right. 5. 5 is the first term because obviously k minus 1. Anything to the power of 0 is 1. That's right. So that disappears. Well, it just becomes unity. So we've got 5 plus, what would the next term? K is 2, 10, 15. K is 3, 45. All right, what's happening each time? We're multiplying by 3. That's right. Now, this is going up to 12. We don't particularly need to know the n number. Does it affect our rule if we don't know the n number? No. All right. What's important to us is our a value. What else is important to us? Our r value. And what else is important to us? Our n value. Right. So our a value is what? Brian, what's our a value? 5. What's our r value, Dan?
3.
3. And how many terms have we got, Max? How many terms? 12. 12. Okay, so we need to substitute into the sum of the geometric progression. Anybody remember the sum of the GP formula? Sum of the GP.
A times 1 minus r to the power
Right. A times 1 minus r to the
of n,
n over
and then a 1 minus r.
1 minus r. Good. Okay. So that's the sum of the GP. So we need to substitute those values in. So we're looking at the sum of the 12 terms, which is 5. 1 minus 3 to the power of 12, all over 1 minus 3. It's a calculator job, isn't it? Right, this grows huge, very, very, very quickly. So, who's going to provide the number? 1,328,600. Okay, 1,328,600. Okay, massive number. Okay, have a little look at the one below on your sheet and think about how you could do that one. Now it looks like I've copied the same question again, doesn't it? Look a little bit closer. What's the difference? Right. Right, it starts at k is 5, but unfortunately, we've got a couple of different ways of doing this question. You might like to utilise what you've already done. All right, I'll get the question up in front of us again. So this particular question, very, very similar, but the start value on the summation has altered. It's K is 5. Let's have a little look. Lorraine just suggested that we started at K is 5. So we started resubstituting some numbers starting at 5. That's one way of doing it. Set up a brand new geometric progression.
Can we
Any
just-
other ways?
Can we just use another value for A?
We could do, that's what Lorraine was suggesting. So we could start off with a brand new geometric progression, new A value, same R value, and work out how many terms.
Or can you subtract 1 to 4?
Yes, that is a marvellous idea as well. Okay, we could use the answer that we've just generated and subtract the sequence K is 1 to K is 4. That would work just as well. I'm just going to go over this last one here. Right, we wanted from 5 to 12 inclusively. Now, when you, this is only one way, I stress one way of doing it. The way that Lorraine and Max suggested was equally as good, and it would work just as well and give you exactly the same answer. So that often happens in maths. You've got two routes, but you get exactly the same answer at your destination. So the one thing you have to make sure, what I've done is I've looked at the summation from 1 to 12 and I subtracted the summation from 1 to 4. You've just got to make sure that you don't include 5. That is important because this one starts at 5. So you've got to go up to. Now, we're only including integer values. So we know that we haven't intruded on anything to do with the one that we actually want. Right, now I don't particularly need to write that one out because I've got all the information other than perhaps what the first term, how many terms are involved, but I can easily establish that from the actual summation value. So I know that A is going to be 5. D rather. R is going to be 3, and the number of terms is going to be 4. So I'm substituting that into my formula. A bracket 1 minus r to the n over 1 minus r. 5, 1 minus 3 to the power of 4 over 1 minus 3. If I work that out, what value did I get? 200. That's right. So the answer that I should get for the total 132,840. Okay? So that's just one way of doing it. Okay. So while you're, if you've managed to get that and there's no more questions, then have a look at question 3A and 3C on the sheet. I'll come around and have a little look to see how you got on. Just make sure you're all okay. Right. Any problems with this? Okay. Right. What you need to do is make sure, I'm not asking that you finish this sheet. What we will do is look at this sheet again next lesson and pick out some further examples to complete. What I would ask is that you have a go at completing the ones on this sheet, the sigma notation. Alright, it is important that you get to grips with that, especially with the alternating sequences. Okay. Right, okay, pop your stuff away please.